Welcome back to our math video series. Today's topic is on circular functions. We'll look at coordinates of points on the unit circle, talk a little bit about reflection. Also we'll find function values using the coordinates of those points, and we'll leave the graphing of the 6 trig functions for another time. So we'll just focus on those first two outcomes. To begin with, what in the world is a circular function? Circular functions are, for example, the relationship between cosine and sine, I guess, on a graph. If I take a look at this little Excel spreadsheet that I whipped up, I put angles over here, then I determine the cosine of those angles and the sine of those angles. And then I graph those as ordered pairs around this on this quadrant. And what popped up was a circle. If I would have put more degrees in there, more angles, I would have got actually almost, it would have looked like a straight or a line, a perfect circular circle going around. Essentially how I think of circular functions is that they repeat themselves. In other words, I have a point here and I can see a point over on this other side. And this is what some people refer to as a reflection. So a reflection on here, the y-axis. But notice also I have a point down here that's similar. So I can reflect on the x-axis. Or there's a point over on this other side right there, which is a reflection across the origin. If you look at my points that I've got here, I've indicated a number of ratios that keep popping up. For example, 0.5, 0.5, 0.5, 0.5. There's a couple of them that are negative, but the ratio itself is similar. It repeats. If you look at every one of those and what the cosine ratio is, I should have underlined those, but 0.5 always goes with 0.87, 0.5, 0.87, 0.5, 0.8. So they always go together. If I looked at these ones, they would also go together. And that's part of what they mean then by a circular function. So our purpose today is to take a look at what some of these points are. And if we know some of these points, it helps me determine what all the rest of the points are, because they're simply reflections of this initial quadrant. So let's take a look specifically at them. So let's take a look at what the value of cos and sine are for each of these angles in the first quadrant. And then we'll see what those points would be for the other quadrants as well. Notice that rather than plotting points as x and y values, I'm plotting them as cos theta and sine theta values. So over here, and if you want to follow along on your calculator, you certainly can. This, of course, is our initial arm, and if I call it also my terminal arm, the angle measurement would be 0. If I ask for what the cos of 0 is, you'll find that it comes out to 1. If I find what the sine of 0 is, you'll see that it is 0. And that's my point. While we're on those ones that are right on the axes, let's do this one up here too. If you do cos of 90 degrees, you'll find that it comes out to be 0, because the x value of this point is 0. If I want the sine of 90 degrees, I just find out what y is at this point. If it's a unit circle where the radius is 1, then this point will be 1. Now, similar points can be found all over here. So if I do the cos of 180, you'll find it's negative 1. And the sine of 180 is 0. Down here, you're probably already filling in the cosine of this. Since x is 0, cos is 0. And since y is negative 1 there, sine of 270 degrees will be negative 1. But let's fill in these other ones. And when we fill these in, you'll notice that over here in quadrant 2, quadrant 3, quadrant 4, I'll be able to fill in similar values. just as we did with the ones that are on the axes. So here, if I figure out what the cos of 30 is, you'll find that it's 0.866 on your calculator, but also I could use my little handy dandy formula down here to do that. Cos of 30 is adjacent over hypotenuse, so cos of 30 is root 3 over 2. Sine of 30 is 1 over 2. Now, remember I was talking about reflections? So that's the value of this point right there. If I were to go over to this point that's straight across, not perfect, but straight across from that, you'll find that the ratios are identical. Root 3 over 2 and 1/2. This one down here, same thing. Root 3 over 2 and 1/2. This one right over here, another reflection, root 3 over 2 and 1/2. The only thing that I haven't put on the rest of these is whether they're plus or minus. And I do that just what x and what y would be. In this quadrant here, x is negative, so that means this part of the ratio is negative. Y is positive, that one's okay. In this quadrant, they're both negative. Both x and y, or both cos and sine are negative. In this quadrant, x is positive while sine is negative. But do you notice that the ratios are the same? They repeat themselves going around this circle. If I go over to 45 degrees, cos of 45, here's my 45 degree, cos is 1 over root 2. 1 over root 2. And the sine is also 1 over root 2. I'll bet you're already seeing what I'm going to do here, and here, and here. They'll be the same coordinates, but they'll have appropriate signs in each quadrant. And similarly, 60 degrees. Cos of 60 degrees is 1/2. I can see that here. Here's my 60. Cos of 60 is adjacent over hypotenuse. And the sine of 60 is root 3 over 2. Again, I can see that on my triangle here. Sine is opposite over hypotenuse, root 3 over 2. And you'll have similar reflections here, here, and here. So you'll have the same coordinate with just some different signs. So this should help us when we are going to determine exact values of trig functions or of trig angles. Here's some steps that I've sort of found useful when I'm having to find exact trig values. First, what I do is I find the angle on the quadrant somewhere. So I find it, maybe it's over here somewhere. Then I find whatever the reference angle is for that. So the reference angle is always the angle it makes with the x-axis. And then from either the chart, a chart that may be in your textbook, or from the unit circle coordinates, or from your handy dandy triangles, determine what the ratio would be at that point. And then determine whether it'll be a positive or a negative, depending on which ratio and in which quadrant you find. So let's try a couple examples. Here's one. They want to know the exact value of the sine of pi over 6. So what's the exact trig ratio for the sine of pi over 6? Well, first thing I need to plot that. Pi over 6, I believe, is right about there, where this angle here is 30 degrees. I could find that out if I wanted to by, as we've seen in other videos, multiplying this by that ratio, 180 over pi. The pi's cancel, 6 goes on 180, certainly 30 degrees. So I could convert it to degrees first and then sort of figure out where it is. Now if they want to know what the sine of pi over 6 is, all I have to do is find out, let me erase this, all I have to do is find out the sine of 30 degrees, which I could, if I want, use my little triangle. Here's 30 degrees here, sine is opposite over hypotenuse, so it's equal to 1/2. I'm in quadrant 1 and y is positive there, so this will be a positive 1/2. I could have, if I wanted to, gone back to that unit circle. So 30 degrees is right here, and the value of sine is the second coordinate in that point, which is a half, like we saw. Let's try another one. Cos of 2 pi over 3. Again, I can figure out where that angle is. Let's just do that. 2 pi over 3 times it by 180 over pi. The pi's cancel. 3 into 180 goes 60 times 2. I'm calling it 120 degrees. So 120 degrees would be 90 plus another 30. So about there. That's my 2 pi over 3 angle. Or it's a 120 degree angle. But in my steps I said that we need to determine what the reference angle is. That's this angle. So if this is 120, what would this be? Sure, 60 degrees. So now I go to my handy dandy little chart down here, and what I'm wanting to do is find the cos of 60 degrees. So the cos of 60 degrees is adjacent over hypotenuse, or 1 over 2. So the cos of 2 pi over 3 will be the same as the cos of 120 degrees, if we want to convert it to degrees, or the same as 60 degrees, with an appropriate sign change if need be. So the cos of 60 degrees we've seen here is 1/2. But if I'm winding up in quadrant 2, what is the value of cosine or of x in quadrant 2? Yeah, it's negative. So the value of cos of 2 pi over 3, the exact value will be negative 1/2. Again, I could look it up on my unit circle. Look up my 2 pi over 3, that would be this point right here. And this point corresponds with this one here, sorry. This point corresponds with this one. So that is 1/2 and root 3 over 2. And since we're in this quadrant, cos is negative. So I asked for what the cos of this was. So cos is the first value, negative 1/2. And that's what we determined too. Let's try one more. Sine of 7 pi over 6. Again, I could do my calculations here. You can maybe trust me that that is the same thing as the sine of 210 degrees. Let's find that on the quadrant. It'll be 180 plus another 30. So right about there. So my reference angle here is 30 degrees. So sine of 210 is the same thing as the sine of 30 degrees with an appropriate sign change here if need be. So sine of 30 down here, here's 30 degrees. Sine opposite over hypotenuse is 1/2. Now I just have to worry about whether it's going to be plus or minus. Well, I'm in quadrant 3. What is the value of sine, or what is the value of y in quadrant 3? Negative. So my answer for this question will be negative 1/2. Again, I could look at my quadrant here. Here's my 7/6 pi would be right there, or 210 degrees there. The value of sine there, negative 1/2. So the unit circle can come in handy, but you can also figure all those questions out just using your handy dandy triangles. Sometimes, however, we'll get angles in which they're not exact ones, or they don't care whether you give an exact value. If you get one like that, then you can simply type that out on your calculator. So if I go, I'm using a new calculator here, sine of 56 degrees, and it didn't give it to me. Let me try something else. Okay, that right there, and I want to round the number, so sine of 56. Oh, I think I have my calculator in radians, so let me get that out to, and this would be something that you would go through as well. If I go, I have to get mode, and then, yeah, I'm in radians. So I need to go into degrees. You'd have to do some similar thing. And when I hit enter, then I get 0.829. So if they're not looking for an exact one, I can just give them a decimal. 0.829. Or I can do the same thing here. In this case here, I would either convert my calculator to radian mode and then find the cosine of that, or change this radian measure to degrees. I think it'd be 135 degrees. And then just type that on my calculator and figure out what it is. I believe it's negative 0.707. So that was just a quick introduction to the unit circle and how points repeat around that unit circle. And if I were to graph those points, as we saw in this slide here, the coordinates for cos theta and sine theta of degrees that go around the unit circle do form, indeed, that a circle.